A warm welcome to all. I am Dr. Tejaswi Potluri from the Department of CSC Cybersecurity, DS and AIDS from the College VNR VJEC. As a part of series lectures of Computer Organization and Architecture, today let's see about the multiplication algorithm in sign magnitude representation. In today's lecture, we are going to cover about what are the hardware components we require to complete the multiplication algorithm and the flow of the algorithm and the step-by-step process along with few work examples. So let's see what is a sign magnitude representation. So first starting with an example of representing -7. So here you can see how to represent -7. So we are going to represent -7 by using a sign magnitude representation where MSB bit will be used to represent the sign. Here we can observe like if MSB bit is 0, we can say it is a positive, and if a MSB bit is 1, it is represented as a negative. So first we need to convert the decimal value 7 into the binary representation, that is 0, 1, 1, 1. So now we have to take one more bit which is considered as a sign bit. Now as it is a -7, it is negative. So we are going to represent the MSB bit as a 1. So altogether the sign magnitude representation of -1 will be 1, which is the MSB bit. As it is negative, we are writing it as a 1, and the remaining 4 bits, that is 0, 1, 1, 1, this is nothing but the decimal value of the 7. So in the sign magnitude representation, this we are going to call it as a sign bit, and the remaining is nothing but the decimal value of the 7. So now this sign magnitude representation is very simple to implement, and where only we are going to consider the MSB bit to denote the sign of the value. So now we are going to perform the multiplication algorithm on the sign magnitude representations. So now let's see what is the main key concept of the sign magnitude multiplication. So here we are going to implement a simple shift and add operations to complete the multiplication algorithm. So here before starting the algorithm, we need to check what are the hardware components we require. So we require a few number of the registers. So first let's see how many number of registers we require to complete the multiplication. So as we will be having two values to perform the multiplication, those are the multiplicand and multiplier. So we need two registers which are calling it as a register B and register Q. So as the product requires more size, we require one more register to store the product. So we are considering as a. So altogether we require 3 registers, register B, Q and A. So here we can see like this A is equal to 0, which is nothing but the register. So as this register is used to store the final product after completion of the multiplication algorithm, we are initializing this register to 0. And next coming to the E. E is nothing but a flag which is used to store the carry bit after completion of the intermediate addition during the multiplication. So initially we are making E to 0. And next you can see like SE. SE is also flag which is nothing but you are calling SE as a sequence counter. So this sequence counter is used to store the number of bits of the multiplier which is stored in the register Q, because you are going to repeat the process of the multiplication based on the number of bits of the multiplier. Based on the bit of the multiplier, if it is 1, you are going to follow a series of steps, and if it is 0, you are going to follow other series of the steps. So you are going to repeat the process, entire process based on the number of bits of the multiplier which is stored in the variable SC, sequence counter. So next you are going to check the LSB bit of the register Q, which is nothing but the multiplier. Suppose now if the LSB bit of the register Q, that is if it is 1, you are going to perform addition to the registers A and B, and then you are going to perform shift operation which you are calling together as a shift and add. So successive shift and add will be implemented when the LSB bit of the register Q is 1. Suppose if the LSB bit of Q is 0, instead of performing shift and add operations, you are directly going to perform the shift operation. So here you are going to perform the right shift operation, and the right shift operation is performed to the registers E, A and Q altogether, not only on the single register. So here this shift operation is performed EAQ considering all together as a single value. Suppose if Q naught value is 0, instead of performing the addition, you are directly going with this right shift operation. So now coming to the series of the steps which we are following under the multiplication algorithm are, so first you are going to check the least significant bit, which is nothing but the LSB of the multiplier. Q naught is nothing but the multiplier. So based on the value of the Q naught bit, you are going to take a decision like whether we are going with the shift and add operation or you are going with directly with the shift operation, where you are going to perform a right shift operation, which is logical right shift operation on the values E, A and Q. And next you are going to repeat these cycles for n times. N is nothing but the number of bits of the multiplier which is stored in the flag sequence counter, that is SC. So the remaining steps will be like adding B to A if Q naught is 1, and next you are going to perform the right shift operation on E, A and Q by only one position, and next after completion of this entire process, this will be a cycle. So after completing this cycle, you are going to decrement your sequence counter by 1. So after decrementing the sequence counter by 1, you are going to check what is the value of sequence counter. So you are going to repeat the same cycle for n number of times. That is, it depends upon the size of the multiplier. So now let's see with a simple example here. So now this example is for the product sign calculation. See, for example, if you are multiplying two negative numbers, the result always it will be a positive. At the same time, if you are multiplying two positive numbers, the result always it will be a positive. And if you are multiplying one negative and one positive, the result will be a negative, which we are representing in the form of a binary form here. So as you are storing your multiplicand in register B, BS is used to store the sign bit of the register B. So now, as you are storing the multiplier in register Q, the QS is used to store the sign bit of the multiplier. So now, the sign bits of the multiplicand and multiplier are stored in the sign flags BS and QS. So now here you can see like where BS and QS values are 0 and 0, which represents both the register B and Q are holding the positive values. So if you are multiplying the two positive values, the result always it should be a positive. So now this you can obtain these results by performing the simple XOR operation for the sign flags of multiplicand and multiplier. So now here you are performing XOR operation for BS and QS, which are the sign flags of register B and register Q. Those are nothing but multiplicand and multiplier respectively. So the next example you can see like here you are multiplying one positive and one negative, where your multiplicand is positive and your multiplier is negative. So when one positive into one negative, it becomes a negative, which is nothing but a simple XOR operation for BS and QS. In the same manner, you are going to calculate the sign of the product here. The sign of the product will be calculated based on the XOR operation between the sign flags of multiplicand and multiplier. So here you can see like a simple XOR for BS and QS, which is nothing but the sign of the product. As you are using the register A to store the final product, the sign flag for the product will be represented by using AS. So the result of your XOR operation should be stored into the flag AS, which is nothing but the sign bit of the final product of your multiplication. The same here you can represent in the theoretical form, that is the XOR operation for BS and QS, which is nothing but the AS, which is nothing but the sign of your final product. So this will be the first step of the multiplication algorithm, that is calculation of the product sign. And now next we can see what are the different hardware components we require. So as the previous example we discussed, we require the registers B to store the multiplicand, register Q to store the multiplier, and A which is used to store the final product. So during the multiplication process, the same register A is used to store the partial product. And one more flag, we required a sequence counter to store the number of bits of the multiplier. Along with this, you are going to require a flip-flops or flags, which you are calling it as AS, BS and QS, which are used to store the sign bits. As we are representing the numbers in sign magnitude representation, we require flip-flops to store the sign bits. So along with this, during the addition, you require a flag to store the carry bit, which you are representing by using E. Along with this, to perform the addition between the intermediate values, you need a parallel adder. So the same circuit can be used to perform addition or subtraction for two values. So to perform both addition and subtraction by using the same circuit, you are going to use a complementer along with the parallel adder. Along with this, you need a control logic, that is to check what is the value of the sequence counter, and based upon the value of the sequence counter, we are going to take a decision like whether to repeat the cycle or to stop the algorithm. The same can be represented in the form of a block diagram. Like here we have taken an examples. The multiplicand is 7 and the multiplier is 3. So as a part of initialization, the multiplicand 7 is stored into your register B and the multiplier 3 is stored into your register Q, and the final product is stored into register A. So initially, as we don't have the final product, we are going to use this for the partial product. So initially you can initialize it to 0. And next you are going to have a flip-flops AS, BS and QS, which are nothing but the sign bits of the registers A, B and Q. Along with this, you are going to have a complementer and parallel adder. This complementer and parallel adder is going to decide whether the operation is addition or subtraction based upon the mode bit. Along with this, if you get any carry bit from this parallel adder, this will be pushed into your carry flip-flop, which is represented by using E. And next you are going to have a sequence counter. Here we are initializing your sequence counter with the 4 bits, as the multiplier 3, you are getting 4 bits whenever you are representing it into a binary format. And next you are going to have a control unit to manage the operations, like to check what is the value of the sequence counter and what is the value of your LSB bit of the Q to take a decision. And next here you can see a simple flow diagram of the algorithm. Here it is first initialization registers. So coming to the step initialization of registers, you are initializing registers B, Q, A, E and SC. So in B you are going to store multiplicand, in Q you are going to store multiplier, and sequence counter is nothing but the N, which is the size of your multiplier. And next the registers A we initialize to 0, as initially the partial product will be 0, and next the carry bit also is initialized to 0. And next you are going to first complete the calculation of the product sign. The product sign is calculated by performing a simple XOR operation between the sign bits of your multiplicand and multiplier, which are nothing but BS XOR QS, and the result is stored into your AS. And after that you are going to test or check the value of the LSB bit of the multiplier, which is nothing but the Q0. So if Q0 is equal to 1, you are going to perform shift and add. That is, first you are going to perform the addition operation between registers A and B using parallel adder and complementer, and the result is stored into A, where if you get any carry, it is pushed into E. And after, if Q0 is equal to 0, simply you are going to skip this addition step. And next, the default step is a right shift operation for E, A, Q altogether by one position. So if, for example, here let's see an example, like suppose if the value of E is 1 and the value of A is 1, 0, 1 and the value of Q is 1, 1, 1. Now if you are performing right shift operation on E, A, Q, the value becomes like E becomes 0 and now A becomes, you are going to right shift this E value into A. So now here it is 1, 1 and 0. And next this will be pushed into Q, 1, 1, 1. And the rightmost bit, that is your Q0 bit, will be discarded from here. So this is a right shift operation on E, A and Q. So after performing right shift operation, which is a default step, whether the Q0 is 0 or Q0 can be 1, next you are going to decrement of your sequence counter. So you are decrementing your sequence counter by 1. So after decrementing again, you are going to check the value of the sequence counter. If sequence counter is the non-zero value, you are going to repeat the cycle from the step number 3. If it is 0, the algorithm is completed, the multiplication is done, and the final result is stored into your registers A and Q, and now we can stop the process. So now here we can see a working example. So now here I am considering my multiplicand as a 7, and the sign of the 7 is negative, minus, and next the multiplier is 3 and the sign it is negative, minus. So where as the sign is represented in the flip-flop BS, the value will be 1 as it is negative, and the same case with the QS, the value as it is negative sign, you are representing QS with 1, and the value of your register B is nothing but the decimal binary value of your decimal 7, that is 01111, and coming to your Q, which is nothing but multiplier, simple the binary value of 3, which is nothing but 0011. So as a part of the first step, you need to calculate the product sign. The product sign is calculated by performing a simple XOR operation for QS and BS. So now here you can see you're going to perform XOR operation for QS and BS, which are nothing but 1 XOR 1, which is 0, which indicates positive, and this is stored into the flip-flop AS. So after this, I'm going to initialize all the registers as a step 1. Since step 1 A, which is used to store the partial product. So initially it will be all zeros, and next B, it is multiplicand. Multiplicand is nothing but my -7. But here in the B, I'm going to write only the values of 7 because the minus is represented using a flip-flop. So here I'm going to write down only the binary value of 7, that is 0 triple 1. If it is positive 7, the BS will be 0, but there is no change in your register B, that is the multiplicand value. So next I'm going to initialize the register Q with the multiplier, that is 30011, the same. Even though it is a positive or negative, the value of your Q doesn't change. You're going to change only the flip-flop, that is QS. So now here I'm initializing my Q with 0011, which is nothing but the binary value of 3. And now as the number of bits of the multiplier here, it is 4. I'm initializing sequence counter with 4, which is nothing but bits of the multiplier. So this is the first step of my algorithm. So coming to the further steps. So next I'm going to start my iterations. In the first iteration, I'm going to check what is the value of Q0, that is LSB bit of the multiplier. As the LSB bit of the multiplier, it is 1. Here you can see it is the 1. So if it is 1, first step is we need to add registers A and B. So I'm going to add registers A and B. So the result becomes 0 triple 1. And now the carry bit is 0. So the E value is 0. So after this, I'm going to perform right shift operation for all the registers E, A and Q. So after performing right shift operations, I have decremented sequence counter by 1. So initially the sequence counter is 4 and now it becomes 3. And now again I'm going to check what is the value of Q0. Again here the value of Q0 is 1. I'm going to repeat the same process, that is addition of B to A, and next I'm going to perform the right shift operation on EAQ. So after that I have decremented by sequence counter by 1. So now the sequence counter becomes 2. So now here you can see after the second step, now the Q0 value is 0. So if it is 0, I'm not going to perform any addition operation for B to A. Directly I'm going to the right shift operation. So now here you can see shift only. Now perform right shift operation for E, A and Q. So after right shift, again decrement your sequence counter by 1. Now repeat the process. In the last step, you can see the sequence counter is 0. So now here I'm going to stop my process. And now if I want to check the final product, this is my final product after completion of the multiplication algorithm. So this is a simple example for the step-by-step iterations of the multiplication algorithm for the sign magnitude representation. So now let's see all the key takeaways and the limitations of the algorithm what we have discussed till now. So now we have implemented the multiplication algorithm only for the sign magnitude representation, where we have the alternate algorithms like Booth's multiplication algorithm, which is for the sign 2's complement, which we can see in the next video. Coming to the comparison in the terms of the performance with these two algorithms, you can see is like the algorithm which we discussed right now is a little bit slower than the Booth's multiplication algorithm, which we are going to implement on the sign 2's complement representation. And also we will be having one more algorithm, that is Volcat tree methods. But whenever you are checking with the time complexity of this algorithm is order of n. It means which requires n cycles for n bit multiplier, where n is nothing but the number of bits, that is nothing but the size of the register. So now here just we are going to implement a simple right shift operation along with a simple addition operation, which you require only parallel adder and complementer. And the number of registers we require are only these A, B, Q and sequence counter, and we require a flip-flops to store sign bits, which is not required for the sign 2's complement representation. Coming to your limitations, as discussed earlier, coming to the performance limitations, it is little slower than the Booth's multiplication algorithm, which is used for the sign 2's complement. But if your architecture is going to implement only sign magnitude representation, you have to go with the same algorithm, because the Booth's will be used for the sign 2's complement representation. And also it is only suitable for the fixed point representation, not for the floating point representation. And the hardware requirements will be, we are requiring multiple registers and flip-flops to complete this algorithm. And also we need a separate circuit to complete the sign computation, which is not necessary in the sign 2's complement representation. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.